Hello students, today we'll be learning a new chapter where we'll learn lots about numbers and their properties and also have lots of fun. The chapter is whole numbers. And remember students, don't just sit and watch like a movie. Do get a pen and paper ready with you so that you learn better when you do it yourselves. So let's get started. I think many of you have played with marbles, isn't it? The traditional Indian marbles game is called Kancha or Goliata. You might also have seen or played the brain beta puzzle, which originated somewhere in Europe. In brain beta, following some rules, you keep on taking one marble at a time, such that at the end, only one marble should be left in the center hole. If you ever get a chance to play brain beta, do not miss it. Say we have 50 marbles in this cup. If I take out one marble, how many are left? 49. If I take out one more, 48. One more, 47. Good. We also say that 48 is the predecessor of 49. That is, the number before 49 is 48. We also say that 50 is the successor of 49. That is, the number after 49 is 50. As you might have noticed, predecessor is same as subtracting 1 and successor is same as adding 1. Now, say we have only 3 marbles left. If I take out one, only 2 will be left. If I take out one more, only 1 will be left. If I take away this also, how many will be left? Nothing or 0. What is the predecessor of 2? It is 1. And what is the predecessor of 1? It will be 0. We will learn something new now. Here, we shall put the numbers on a line. So, we call this a number line. Say I mark this point as 5. What will be its successor? That is its next number, 6. After 6, 7. What is the predecessor of 5? That is its previous number, 4. Before 4, 3. Then 2. And finally 1. What is the predecessor of 1? As we saw earlier, it is 0. Here, the distance between any two numbers next to each other is the same, and we call this the unit distance. We know that the numbers 1, 2, 3, 4 and so on are called natural numbers. But now we also have 0. So we call the collection of natural numbers along with 0 as whole numbers. So the whole numbers are 0, 1, 2, 3, 4 and it keeps on continuing. Is every natural number a whole number? Look at the image and try to answer. Yes, as you can see, all the natural numbers are also whole numbers. I have marked 31 on the number line. What number should we mark the fourth point after 31? It is 35. And what number should we mark the fifth point before 31? It will be 26. You can also observe that the numbers on the right side are always greater than the ones on the left. For example, 35 greater than 31 and 31 greater than 26. In the same way, the numbers on the left are smaller than the ones on the right. 26 less than 31 and 31 less than 35. You can see a picture of a clothesline where we put our clothes to dry, but here we have put some numbers instead, that are 546 and 746. There are also some numbers on the top that are hiding. What we should do is, when each number in the top shows up, we have to hang it on the clothesline in such a way that they are in increasing order. That is, they are increasing from left to right. We will see what the first number is. It is 756. So where should we put this? Is it less than 546? No. Is it less than 746? No. It is greater than 746. So we will put 756 on the right side of 746. Next is 654. Now where will this go? It is greater than 546 but less than 746. So we will put this in between those two numbers. Now the next number is 765. This is greater than 756, isn't it? Now it is 645 and this comes in between 546 and 654. Now children, can you check if the numbers on the clothesline are in ascending order? Yes, they are. Now 475. Where does this go? It is less than 546. Now the next number is 564. You can see that this is greater than 546 but less than 645. Now coming to the last number, we will see what this is. It is 456 and this looks like the smallest of all the numbers, isn't it? So where should we put this? In the beginning. Yes. Can you check if the order is correct now? We saw this before, isn't it? What is this? This is the number line for whole numbers. You can also do different arithmetic operations using the number line. Say if we wanted to do 6 plus 2 using the number line, we will start at 6 and move 2 steps to reach 8. We can also do subtraction on the number line. Can you try 13 minus 4? So you start from 13 and go 4 steps backward to reach 9. Multiplication is also possible. If we want to look at 3 into 4, we jump 3 times with each jump covering 4 steps. After the first jump, you will reach 4. Then you will reach 8, which is 2 times 4. After the third jump, you will reach 12, which is 3 times 4. Now explore how you can do division using the number line. If we add two whole numbers, will we always get a whole number? Let us see. We will add 5 and 3, which are whole numbers. We get 8 as the sum, which is also a whole number. We can take one more example where we are adding 20 and 0 and the sum we get is 20. Again, all of these are whole numbers. You can try this for yourself. Take any two whole numbers and see what sum you get. And you will be able to find out that the sum will always be a whole number. So, we say whole numbers are closed under addition. Now we will look at subtraction. We can take any two whole numbers and see what the difference will give. We will take 8 and 6. What is 8 minus 6? It is 2. All these are whole numbers. But when we take 4 minus 7, is it a whole number? No. It is minus 3, which is not a whole number. These are called integers, which you will be learning in chapter 6. So, a subtraction of two whole numbers need not always give a whole number. Hence, we say that whole numbers are not closed under subtraction. Next is multiplication. We can take two whole numbers, say 3 and 4. The product is 12. Again, all of these are whole numbers. But what will happen if we take 9 and 0? The product is 0, which is also a whole number. As you know that any number multiplied by 0 will give the 0 as the product. You can also try this by taking any two whole numbers and see what their multiplication will give. And the multiplication of two whole numbers is always a whole number. Hence, we say that the whole numbers are closed under multiplication. But what about division? Will the division of two whole numbers always give a whole number? We will check out. Let us take 6 divided by 2. What is 6 divided by 2? It is 3. But what is 7 divided by 4? 7 divided by 4 does not give a whole number, isn't it? So, we say that the whole numbers are not closed under division. Now, have you ever wondered what happens when we divide a number by 0? You know that division is the same as repeated subtraction. For example, 12 divided by 3 is equal to 4 means 3 can be subtracted from 12 4 times. But have you ever wondered what happens when we divide a number by 0? Let us see. We will take 5 divided by 0. Now, we will try to subtract 0 from 5 and see how many times we can subtract. 5 minus 0 is 5. Again, 5 minus 0 gives 5. Oh, this looks like it goes on forever. Will this ever stop? No, never. So, we say 5 divided by 0 is not defined. Hence, division by 0 is not defined. Say, before the lockdown, you and your friend went to a bookstore to buy some books. And after a lot of searching, both of you decided on the same set of 5 books. When preparing the bill, the shopkeeper noted down your books in this order. First, the story book for 30 rupees. Then the drawing book for 25 rupees. Then the puzzles book for 40 rupees. Then the history book for 15 rupees. And finally the kids magazine of rupees 10. But when preparing your friend's bill who also bought the same books, the shopkeeper noted down the books in a different order. We will see what that order is. First, the kids magazine of rupees 10, then the history book of rupees 15, the drawing book of rupees 25, then the story book of rupees 30, and finally the puzzles book costing rupees 40. You can observe that your friend's bill is in ascending order, whereas your bill is in a random order. Now, my question to you is, whose bill amount will be high or whose bill amount will be lower? What do you think? Children, have you ever wondered if changing the order in addition of two numbers, will it give the same sum or will it give a different sum? We will take, for example, 5 and 4. What is 5 plus 4 and what is 4 plus 5? Both are same, right? Both give the same sum 9. Here is a visual representation. The first row has 5 yellow triangles followed by 4 red triangles. Totally there are 9 triangles. The second row has 4 red triangles followed by 5 yellow triangles, which are also 9 triangles combined. Now, can you try adding 6 and 8 in different orders? See what sum you get. You will be able to find that no matter which order we add two whole numbers, the sum we get will be the same. Hence, we say that whole numbers are commutative under addition. Now, we will try the same thing with multiplication. We shall take two whole numbers, multiply them in different orders and see whether the product we get will be the same. Try with the numbers 3 and 4. Calculate 3 times 4 and 4 times 3 and see what products you get. You will be able to see that you will get 12 as product for both. Here is a visual representation. Say you had 12 pebbles with you. In the first arrangement, we can arrange it as 4 rows of 3 pebbles each. And the same 12 pebbles we can also arrange as 3 rows of 4 pebbles each. Now, try multiplying in different order the numbers 5 and 7. See what product you get. You will be able to find that the whole numbers are commutative under multiplication, as we get the same product even if we change the order. Now I have a task for you. You have just verified the commutative property for addition and multiplication. Now what I want you to do is, you can check the commutativity for subtraction and division also. So you can take two whole numbers, subtract them and divide them in different orders and see whether the answer you get will be the same even if you change the orders. What if we had three whole numbers to add? Now will the order matter? Let's find out. Let us take 2, 4 and 7 and add these in different orders. In the first one, we are adding 2 plus 4 the first, and in the second one, we are adding 4 and 7 first. You will be able to see that no matter what order we solve, the sum we get is the same. You can also try this for yourselves by taking any three whole numbers and adding them in different orders. We can see that the whole numbers are associative under addition, as we get the same sum even if we change the order of solving. Now, coming back to this question, whose bill will be high or whose bill will be low? What do you think? Both the bills will be the same, isn't it? In fact, the shopkeeper need not even calculate the total 2 times, first for you and again for your friend, as both of you had purchased the same set of books. Now let us look at multiplying three whole numbers. What do you think will happen? Let's find out. We will take 2, 3 and 6 and we will multiply them in different orders. The first time we will multiply 2 and 3, and in the second method we will multiply 3 and 6. What product will we get? Both of them give 36 as the product. You can also try this for yourself by taking any three whole numbers and see by solving it differently, will you still get the same product or not? You will be able to find that the whole numbers are associative under multiplication, as we get the same product even if we change the order of solving. But what about subtraction? Is subtraction also associative? Let us find out. We will take 8 minus 4 minus 3. In the first, we will subtract 8 minus 4, and in the second, we will subtract 4 minus 3. What do you think will happen? Will you get the same final answer? No. You will be able to see that subtraction is not associative for whole numbers. Now, can you tell what happens for division? Let's find out. We will divide 16 divided by 4 divided by 2. First, we will do 16 divided by 4, and in the second, we will divide 4 divided by 2. Did you get the same final answer? No, right? So, we can say that division is also not associative for whole numbers. Till now we have learnt number line operations, closure property, commutative property and associative property of whole numbers. Now let us look at a number magic. We'll have lots of fun. Here are some numbers arranged in a table. I want you to take down this table in your book or a sheet of paper. I will be giving the instructions now. The first one is pick any unstriked number. As none of the numbers are striked, you can pick any number. Once you have chosen, note down your number and then strike out its row and column. Then you repeat steps 1 and 2 until all the numbers are striked. I will show you an example. Say you picked the number in the green box. You strike out its row and column and also note down the number in the green box. Now, from the remaining boxes, choose any number. Strike out its row and column and then note down the number in the red box. For our third number, choose any number from the unstriked boxes. Again, strike out its row and column and note down the number in the yellow box. Now you can choose any number from the unstriked boxes. Oh, but there is only one box left. What should we do? There is no other choice. You can select that. Again, strike out its row and column and note down the number in the blue box. As you can see, we cannot choose any more boxes as all the boxes are striked. Here comes the most interesting part, that is the magic trick moment. I want you to add the 4 numbers that you have noted down and see what total you get. I don't know what numbers you have chosen, isn't it? Yes, of course. But I can tell you the total that you have got is 106. Wow, surprising, isn't it? How was I able to tell what total you have got? You can try again this time by choosing a different set of numbers and calculate the total. See what you get. You will be amazed to see that you get the total 106 again. Let us try choosing different numbers this time also. What is the total? Again 106. Wow! What is happening? Here is a number chart of numbers 1 to 100 and the red square box size is 16, having 4 rows and 4 columns. You can place this red box anywhere in this chart and repeat the trick. Once you have fixed the red box, each time choose different numbers from the red box and see if you will always get the same total for that red box chosen. You can also increase the size of the square box. Here, the green box size is 25, having 5 rows and 5 columns. Try for different boxes and see what total you get. Will the total for a box always be the same, no matter which numbers we choose? you will see that this is indeed a magic trick. But kids, remember, we call something magic only when we don't understand why is that happening. So now is the time for you to look deeper and find out the reason behind this magic trick. Do share this amazing magic trick with your friends and family and surprise them. So we will meet in the next session and I will show you why this magic trick works and we will learn some more properties of numbers.